cardiovascular function, right? So, VO2 is dependent upon the cardiac output times the AVO2 difference, which you now know what that is, right? How much is extracted by the muscle, the tissue bed. Okay, so that describes the relationship between metabolism, which is VO2, and cardiovascular function, which is obviously cardiac output times AVO2. Okay, and I've just broken it down here even further. The VO2 was heart rate times stroke volume, which is cardiac output, times AVO2 difference. All right? That's the big equation. Not to be confused with the fixed law of diffusion that we spoke about on Monday. This is the big equation. Same guy. Obviously, in terms of the cardiovascular response to acute exercise, the things that are going to change in terms of the increase in blood flow to the exercise muscle are obviously going to be heart rate, stroke volume, cardiac output, blood pressure, blood flow, etc. Okay, no surprises there. Steady state heart rate. Steady state heart rate. So when your workload is constant, right? Heart rate rapidly increases until it reaches a plateau. That's obviously what we mean by steady state. That's not rocket science, right? Now, what does exercise training do to your steady state heart rate for a given sub-maximal workload? Now, I've used an example, so even though this is VO2, this could also be heart rate, right? You'll see something like this. In exercise, heart rate starts to go up. And let's say we're just on a track and we're running, a 5-minute mile, but we're doing it steady. We're going to see something like this, whether it's VO2 or heart rate, or even cardiac output, or even stroke volume. What's exercise training going to do to that curve? Let's say this is heart rate. Will it change at all? So we monitor heart rate at the beginning of an exercise training program, and then 8 weeks later we come back. And so what we do, let's say, for this example, we ran this person on the track for a mile, 7-minute miles for a mile. Just got a Garmin on, right? You can locate the pace. You're doing 7-minute miles. Boom. And that's the heart rate. After 8 weeks of training, good training, bring it back in, do exactly the same thing. Run on the track, 7-minute miles for a mile. Is there going to be a change? So I was going to plot the second curve. What would it look like?
It's going to shift to the right.
Shift to the right? How shift? What do you mean?
The steady state would be at a lower workload, I guess?
Right. You'll be down with it. It'll be decreased. So for the same workload, your heart rate's going to be decreased. You're fitter. That person's fitter. Okay? More efficient. And if we put a K2 on them and measure the VO2, like we have here, that would also be decreased as well, right? Similar sort of thing here, heart rate versus increasing power output. I'm not taking the two subjects. This is out of your book here, but this is using on cycling. We've got watts here, power. 0 to 250 watts. Here's heart rate. We've got our option uptake here. Which person here, A or B? I'm not sure what this is actually. Well, this is two subjects, so it's not the same subject. So it's two subjects. Which person's more efficient? Which person's more powerful? Obviously, A, right? At the same heart rate, power output's 250 watts compared to maybe 205 watts. Okay? That's very different. Stroke volume. Okay. We've mentioned stroke volume before. End diastolic volume minus end systolic volume. It's the major determinant of cardiorespiratory endurance capacity. Factors that affect stroke volume is obviously the volume of venous blood returned to the heart, venous return. And know that we call that preload, right? So stroke volume, go back to my crude heart. Okay. You've got the vena cava, you've got all the veins coming in, right? That's what we mean by venous return. What's blood flow that's returning to the heart? What's that going to be determined? What's that going to be determined from? How much blood's returning to the heart? What can affect that? Sorry? Yeah, possibly blood pressure. Blood volume. What's going to determine how much blood's returning? What's going to affect blood volume? Environment, humidity, heat. So if you start to lose plasma volume, for instance, you've gone for a 2-hour run in the heat, your plasma volume's going down. Okay? Your plasma volume's going down, your blood volume's going down, your venous return is going down. Therefore, your stroke volume is going to go down. Yeah? And therefore, your preload is going to go down. Make sense? Kind of just step it back. What determines these factors? Okay? Ventricular distensibility. Really meaning how malleable, how compliant are the blood vessels downstream. Okay. So if you've got a lot of disease, atherosclerosis, and very stiff arteries, that's going to play a role in terms of how much blood you can expel. And we term that arch load. Okay. Ventricular contractility. Sympathetic innervation to the heart. Remember? To the ventricles only. Only. If you increase sympathetic drive to the ventricles, you're going to increase stroke volume, how much blood you can expel, because you're increasing the force of contraction, right? Makes sense? Okay. And I've just mentioned number 4, aortic or pulmonary artery pressure or the afterload. Kind of goes hand in hand with number 2. Okay? Increase the afterload or the resistance downstream, you're going to compromise stroke volume. Obviously, how much blood you can expel. Okay?
If you increase the afterload, the stroke volume?
Absolutely. Because the heart has to work harder, okay, and it can't force as much blood out because there's higher resistance downstream. Okay. Does that make sense? Of course, stroke volume would increase with exercise. Okay, stroke volume of course increases with exercise because your sympathetic drive is increasing. I've already mentioned that. More blood is returning to the heart. Okay, and you're innervating the AEB and SA node with a sympathetic drive, increasing heart rate. So if you increase the heart rate, increase sympathetic drives, increase venous return, that will increase stroke volume. Stroke volume does increase with increasing work rate. It usually plateaus about 40 to 60% of the O2 max. It starts to plateau. Okay. And it's very much influenced by body position. Or if you like, postural differences in venous return to the heart. I think I've got a slide coming up on that. Next slide. Okay. Stroke volumes for different states of training. So, of course, you'd expect stroke volumes to be higher in highly trained individuals compared to trained or untrained individuals. Okay, and these are just some numbers here. Here's resting stroke volume. Here's stroke volume at max exercise. They all increase as you become fitter. And these are just graphs to show you the difference here. Here's stroke volume, for instance, pre-training versus post-training. So this is within a subject here. Then there's pre-training, there's post-training. Stroke volume goes up to any speed on the treadmill. This is real data here. So does end diastolic volume, post-training compared to pre-training. So your EDV's gone up, your preload, and also your ejection fraction. You can expel more. Okay. I just mentioned that you can change your stroke volume based on your postural change. Here's an example of rate of work here, supine versus upright. So you can see with the upright individual, there's no change in end systolic volume compared to someone lying down in the supine position. But the person in the supine position, their EDV, end diastolic volume, has increased compared to someone who's upright, which means then, of course, their stroke volume will go up. The question is, what's going on? Why is this occurring? Why are we getting an increase in EDV lying down compared to standing up? Good. You know the resistance to gravity, right? You haven't got a gravitational pull, okay? So your heart doesn't have to work against gravity to pump blood. So that increases your venous return, the amount of blood that's coming back to your heart. You're not working against gravity. Okay? Okay, explanations for the increase in stroke volume during exercise. Well, we've mentioned this already. If you've got an increased volume of blood that enters the ventricle, which we call preload, it causes it to stretch more, and therefore we can contract more force. That's the French-Starling mechanism, which we spoke about on Monday. Okay, so that's really what we're talking about here. Okay, increased ventricular contractility, which you mentioned on Monday, and I've drawn crudely here. Sympathetic drive or innervation to the ventricles. If you increase the sympathetic drive to the ventricles, you're going to increase the force of contraction. That's what number 2 means. Decreased total peripheral resistance, or the afterload, right? Resistance downstream. That can be increased during exercise because of increased vasodilation of the blood vessels to get to increased blood flow. That will decrease the afterload. Okay? Decrease the afterload. So we saw something like this before here, the Frank-Starling curve, where we had the normal at rest here, right? Here's stroke volume versus the EDV. We saw that on Monday, and we can move the curve from B to A with exercise because of an increased contractility. Okay. Somewhere where you don't want to be, obviously, is down here, C and D, where you've got heart failure or cardiogenic shock. But we're not going to talk about that. Okay, we're talking about this part of the curve. Now, there is conflicting research on stroke volume during exercise. It's not as simple as we think. Okay? The reason I'm saying that is because here's real data of stroke volume versus heart rate. Red is the untrained individuals, so they increase their stroke volume up to 110 beats per minute in this case. This starts to drop a bit. It's not unusual. In blue is a trained individual, or individuals. And as we said, after about 40 to 60% of VO2 max, they start to plateau. However, with some elite athletes, their stroke volume continues to go up. It doesn't plateau. And these guys are up around 100 and probably 185 beats per minute right here. And that's continually increasing. We're unsure why that's occurring. Okay? We're unsure. It may be due to continual sympathetic drive, increasing the force of contraction, but we're unsure. But it does occur in some elite athletes. It's not a plateau. Okay? No surprises in cardiac output, of course. This it's dependent upon stroke volume and heart rate. As you increase exercise, or the percentage of VO2 max, obviously your cardiac output's going to go up. Okay? And we've already mentioned it can go from 5 litres per minute up to even 40 litres per minute in some very elite endurance athletes. It can obviously be trained. Okay? This here is just a little schematic here showing the values. Cardiac outputs depend, of course, on, as you know, heart rate and stroke volume. Heart rate, as you know, is dependent upon parasympathetic and sympathetic innervation to the SA and AV nodes, right? Which I have drawn here. Here they are, right? And stroke volume, as you know, is dependent upon end diastolic volume, okay? Very much so. And of course, end diastolic volume is dependent upon, we just spoke about it, venous return. Increased venous return, increased EEV, increased stroke volume, increased cardiac output. Okay. All things that will occur during exercise. Okay, let's look at some points gained. Blood pressures. I don't really want to spend a lot of time on blood pressure. We spoke about mean arterial blood pressure the other day. Mean arterial blood pressure is dependent upon what factors? Mean arterial blood pressure is dependent upon resistance, total peripheral resistance, and cardiac output. Cardiac output. Okay. We mentioned systolic blood pressure before. It increases in proportion to exercise intensity. So systolic tends to go up. Diastolic blood pressure does not change significantly during exercise. It tends to flatline. And sometimes we've even seen it go down. Systolic blood pressure does go up. It doesn't matter. Okay. And obviously MAP has to go up. It has to facilitate blood flow during exercise. It has to go up. Okay? Because it's dependent upon cardiac output. So if cardiac output goes up, mean arterial blood pressure goes up. Okay? Okay. Redistribution of blood flow during exercise. Important, blood flow is redirected from areas where it's not essential, where it's not needed, like the gut, for instance. Okay? And it's going, where is it going? It's going primarily to skeletal muscle during exercise. So, during exercise then, we see an increase in muscle blood flow. We see an increase in skin blood flow, primarily in hot environments. That's important because we need to offload heat. We're going to talk about that again down the road. Kidney blood flow goes down. It's considered a non-essential organ, particularly when we're exercising hard, particularly in the heat. And blood flow to what I call the non-essential organs, liver, stomach, intestines, etc. And this is all accomplished primarily by the sympathetic nervous system. Remember all those blood vessels? And we know that blood vessels contain blood. How's that all being redirected? How's that being shut off? By the sympathetic tones, right? Remember I said there's only sympathetic drive to the blood vessels. If you increase sympathetic drive to the blood vessel, we've got vasoconstriction. If you decrease it, we've got vasodilation. So where blood is going to be a factor played by, it's going to be under the sympathetic nervous system control. If we need to stop blood flow or limit blood flow to the non-essential organs during exercise, like the liver, stomach, and intestines, we're increasing sympathetic drive to those blood vessels and constricting them down, limiting blood flow. We need to open up blood flow to the muscle. We're going to have less sympathetic drive going to the blood vessels in the muscle, and they're going to be opened up. Okay? Okay, we will come back to cardiovascular drift. We're going to talk about it now, introduce the concept. We're going to talk about it again. We're going to talk about thermoregulation. But there's a phenomenon that occurs in athletes, particularly endurance athletes. In this example here, we've got some guys probably doing like, running 100 miles in the desert, okay? This cardiovascular drift does occur, this phenomenon does occur in hot environments, at basically at constant workloads, constant exercise intensities. So what we're seeing here is a gradual decrease in stroke volume and an increase in heart rate. You see an increase in the fractional cardiac output directed towards the skin circulation. We need to get the blood to the skin as quickly as possible to offload heat. So cardiac output is being directed away from skeletal muscle to the skin in a hot environment as you exercise. Okay? We do see some decreases obviously in blood volume because you're losing plasma volume. So there's an example of some real data here in the lab. We've got during exercise in the heat for 50 minutes. And they've measured heart rate, cardiac output, blood volume, arterial pressures, pulmonary pressures, and stroke volume. The ones to look out for here is, let's look at heart rate. So this is in the heat, heart rate goes up. 20, they take them every 10 minutes, 20, 30, 40, 50 minutes. For a 50-minute duration in the heat, constant workload, heart rate has gone up. So they probably said either this is probably on the site, let's maintain 100 watts in this environment. Don't deviate. We want to see what's going to go on with heart rate, stroke volume, etc. Okay. So heart rate's gone up. Heart rate's gone up. And the other one to look for is stroke volume has gone down. They're sweating. So if they're sweating, right? So if they're sweating, sweating in the heat, what's that doing to venous return? What's that doing to blood volume? It's going to go down. What's that going to do to venous return then? Don't be shy, guys, come on. Shout it out. It's going to decrease, right? You decrease venous return, what are you going to do? End diastolic volume. Decrease. Decrease end diastolic volume, we can do the preload. Decrease, up, down, no change, down. We can do the stroke volume. Down. Right? So, what we've got going on here though, what's interesting is if you look at cardiac output, red, remain constant. Right? So, as you know, cardiac output equals heart rate times stroke volume. So even though stroke volume has gone down, to try and keep the heart rate, the cardiac output level, constant, heart rate has gone up. Therefore, we see no change in cardiac output. So this is what we mean by cardiovascular drift, right? Heart rate's going up, stroke volume's going down, but because of that, we're maintaining a level cardiac output, which is a good thing. Okay? Because we need that blood flow to go where it needs to go. It needs to go to the muscles, it needs to go to the skin, etc. The body's trying to maintain a constant cardiac output. And it does that. Stroke volume goes down because it does go down because of these factors, increased sweating, moving plasma volume, etc.
Is that like a part of like homeostasis?
Yes, exactly. just like a homeostasis. Your body's trying to maintain a constant pH, or constant calcium levels, or maintain a constant cardiac output. Absolutely.
So what would be the benefits to working out?
Benefits?
Yeah, to your body, like lower lines of endurance.
We are going to talk about those again in terms of adaptations, but some of the benefits are you're going to be, you need to become acclimatized, for instance, right? So to become acclimatized, one of the big ones for working out in the heat is you're losing a lot of sweat. Okay? So sweat's comprised of electrolytes, for instance, right? So as you become acclimatized in the heat and adapt to the heat, your sweat, if you like, is more dilute. You're not sweating out as many electrolytes like sodium, potassium, calcium, etc. like that. So that's an adaptation. And that's why, for instance, when I used to go and compete in Hawaii Ironman, for instance, when I was a professional triathlete, I used to go out there 10 days before to, one, to get used to the heat, but two, to primarily adapt. So I'm still going to sweat. That's not going to go away, whether I'm there for 3 weeks or 5 weeks. What's going to change, I'm going to sweat a more dilute sweat, if you like. And it's going to be less concentrated in those electrolytes. So I'm going to lose less of those important electrolytes. That's one example. And we'll talk about those again. Down the road. Okay. We've already mentioned the oxygen content of the blood. Okay. So there should be no surprises there. There's no surprise harmonics at the bottom of that slide. We spoke about changes in the AVO2 difference, right, because of exercise. Obviously, as you, this is out of your textbook here. Here's the O2 again. O2 mLs for 100 milliliter of blood. Here's the oxygen uptake. Obviously, exercise intensity is increasing in this direction. The arterial content of the blood does not change in terms of exercise intensity, but it stays the same. Whatever's coming down to the muscle is the same. What's extracted is going to be different, right? So as exercise intensity increases, you're going to extract more oxygen. Therefore, you're going to get a widening of the AVO2 difference. Makes sense? Plasma volume during exercise. We've already spoken quite a bit about plasma volume. We do lose it, of course, because we sweat a lot, particularly in the heat. It can also move from the blood to the interstitial space, and the blood pressure particularly goes up. So I've mentioned, for instance, certainly that we can lose PV in sweat, especially in hot environments. We do see a 10 to 15% reduction in PV with prolonged exercise. It is lost in proportion to intensity with resistance exercise. You increase resistance exercise, you increase more plasma volume. Okay? We all know, we're going to talk about it again, excessive plasma volume loss can result in impaired performance. In terms of, certainly with resistance training, we can lose plasma volume. We can lose it because of high blood pressures. High blood pressures can move plasma volume into the interstitial fluid. It can drive it into the interstitial fluid with the high hydrostatic pressures in the blood vessel. Okay. This is actually a textbook. You'll figure it out of your textbook here. I don't want to get hung up on it too much. But basically, not only do the hydrostatic pressures play a role, high hydrostatic pressures play a role in driving the plasma into the interstitial space, also metabolic waste products of the active muscle. So lactate is one. Okay. They can also draw water out of the capillaries into the muscle. We mentioned some of those waste products before. Histamine's one, adenamine's one, lactate is one. They can all draw water out of the capillaries Well, we already mentioned this a little bit, well actually quite a bit on Monday. Central regulation of cardiovascular control during exercise is very similar to the idea of blood pressure regulation. Okay? We have that central command in the higher brain centers. We have the control center here, so that's the hypothalamus. We have the control centers in the brainstem. We have information coming in from baroreceptors, for instance. Excuse me, information going out to blood vessels via the sympathetic nerves. Information going out to the heart. Okay, again via sympathetic and parasympathetic drive. Okay, and information coming into the central control center again, obviously information from chemoreceptors, CO2, pH, O2, and mechanoreceptors like stress receptors, etc., even the blood vessels feeding information in. Kind of along the lines of blood pressure regulation. This is a slide not out of your textbook, it's one I put together a long time ago, but basically kind of ties it all together. So in terms of exercising the VO2 max at the top there, and what's determining that? We're talking about endurance, training for long-term endurance, for instance. Okay? An adaptation to endurance exercise is actually an increase in plasma volume. That's an adaptation. So is an increase in red blood cell mass. That's obviously going to increase blood volume. If you increase blood volume, you know, right? You increase venous return. Another adaptation to endurance training, we talked about it, is left ventricular hypertrophy. So an increased ventricular volume. Those two there, of course, are going to increase end-diastolic volume. If you increase end-diastolic volume, you're going to increase preload. If you increase preload, you're going to increase your maximum stroke volume. If you increase maximum stroke volume, you're going to increase your maximum cardiac output. You go back further on and also say, as we spoke about it in previous lectures, we got ready for exam 1, that also an adaptation to endurance training is increased capillary density. Because your muscles want to extract more O2. And that's the actual physical term for that's angiogenesis, right? We're making more capillaries. Capillary bed is increased. So increased muscle capillary density, increased maximal cardiac output, so increase your maximal muscle blood flow, oxygen delivery is going to be increased, therefore VO2 max. Okay? And I'll let you go through the one on submaximal steady state exercise. It's very, very similar. Okay? Okay, last couple of lectures here on pulmonary ventilation during dynamic exercise. All right, so with the onset of exercise, there is an immediate increase, and it's neurally mediated, there's an increase in ventilation. Okay? Obviously, as exercise increases, we've spoken about it before, we have increased metabolism. And what does that do? It generates a whole bunch of CO2 and lactate, etc., right? But primarily CO2 and protons, what do? They stimulate the chemoreceptors, right? The central and the peripheral chemoreceptors. Okay. That information, like you saw on a couple of slides back, all goes to the respiratory centers. Okay. Now, changes occur in the respiratory centers, okay? And then pulmonary ventilation returns to normal at a slower rate. We know that when exercise ceases. But all this information, particularly the CO2 and hydrogen ions, that's all being assimilated by the respiratory centers in the brainstem. And then the respiratory centers are sending out all that information to make a variety of changes if necessary. Increase contractility of the diaphragm, maybe one. Slides coming up on this. Okay, ventilator equivalent for oxygen. You probably have not heard this before. We can measure this in the lab very easily with a metabolic cart. The computer spits this information out to us all the time, breath by breath, and we use it a lot to determine if a person is close to maximum exercise. Also, we can use it to determine if someone's close to their anaerobic threshold or the lactate threshold, which we're going to talk about in a second. So ventilator equivalent for oxygen, there's also one for CO2 as well. Let's just talk about O2 for now. This is the ratio between minute ventilation, VE, and VO2. And it can indicate breathing economy to us. And at rest, that ratio is around about 23 to 28 litres of air per litre of O2. Okay? The maximum exercise goes up, and we're up to about 30 litres a minute. It goes up primarily because you're driving up your minute ventilation. So if you drive up your minute ventilation more than your VO2, that's going to increase. That number's going to increase. Okay. Generally, VO2 remains relatively constant over a wide range of exercise levels until you start getting above the lactate threshold or the anaerobic threshold. It's driven up. Okay, because of this, it's driving up VE, because VE is being stimulated by, and we'll talk about this in a second again. So we've got this information coming in, increased CO2, increased protons as exercise intensity increases, okay? Make sense? They're going to increase. That's in blood, of course. That's being picked up by the chemoreceptors, central and the peripheral chemoreceptors, okay? That information is being sent to the respiratory center. And we know where that's located. It's located in the spinal cord, up front of the spinal cord, raising it, right? That then has to make adjustments. What's it going to do with it? What's it going to do about these? They're too high. Right? It's going to send information out to the diaphragm, okay, the external intercostals, and they're going to increase the contractility of those. Right? You increase the contractility of the diaphragm, external intercostals, it's going to result in an increase in minute ventilation. You're going to breathe harder, right? Because your body is trying to get rid of this stuff, CO2 and the protons. So that's the drive, okay? That's the drive. And that's occurring a lot after the lactate threshold, after the anaerobic threshold. Okay, and you can see right here, here is the VO2, this is data from the lab, right? Here's the anaerobic threshold, and it's fairly constant. Before then and after that, it's driven up. The ventilator equivalent of oxygen is driven up because VE is increasing more than VO2. Okay. Now then, comes back to what is the anaerobic threshold or the lactate threshold. I've kind of mentioned it before. I think that in one of the lectures, I think maybe in the other room. Okay. It demarcates the boundary between anaerobic and aerobic metabolism, doesn't it? We spoke about that. You're going to do a lab in the lactate threshold. I'm sure you've done it yet.
It's tomorrow.
Tomorrow? Okay. Now, you're going to do a lab tomorrow on the lactate threshold. You're going to take blood lactate, you're going to monitor blood lactate, and you're going to graph it up against terminal speed, heart rate, whatever. Okay, and you can determine the lactate threshold for an individual. Okay? Well, we can also determine in the lab, we can also determine the ventilatory threshold, which is, if you like, a non-invasive way of getting at the lactate threshold using gas exchange. We don't have to take the blood lactate. Okay? So this is the point during exercise when ventilation increases disproportionately oxygen consumption. So that it occurs approximately at the same point lactate begins to accumulate in the blood. We know that the lactic acid actually of the protons is buffered by the sodium bicarbonate. Sodium bicarbonate is a buffer in the blood that buffer the protons. Okay? So as lactic acid goes up, bicarbonate goes down. Blood bicarbonate levels go down in the blood because it's buffering the protons. Okay? And ventilation increases due to increased CO2 and protons stimulating the chemoreceptors, which I've just spoken about. Right here. Okay? So, here's our ventilation threshold. Ventilation, this could be lactate, it's not. It's ventilation, this from there, against running speed. And you can monitor the ventilation, graph it up against running speed, and we hit here around about 13 kilometers per hour, and suddenly, boom, there's a big upward sweep in ventilation. It's most likely that is the ventilatory threshold. And if you graph that up against the lactate threshold, the chances are, not always, the chances are that they will coincide. So you'll see something like, if that was lactate, and that was, what do you have, run speed? Then you'll see something, and that's ventilation and running speed. You'll see something very similar. That's just a non-invasive way of getting at the lactate threshold. Okay. So there's that example there. This one here, again, is running velocity. Here's the breakpoint on green, and here's the oxygen uptake on the red. So there's not much of a change in oxygen uptake, although it's increasing, right? But we're not really seeing any demarcation point, any change. But we are seeing a change in the ventilation. And because of that, that should now make sense to you, because you're seeing a big change in ventilation, and we're just seeing a kind of a constant rise in VO2, that will increase the VeVO2 past that point. Okay? And this is just looking, this is the same sort of curve here, looking at VeVO2 here, looking at demarcation point, because the big rise in VE, and this example, this is occurring at 75 watts in a particular person. Okay. Okay, last couple of slides here on respiratory regulation, acid-base balance. We've already mentioned about these, we've spoken about these before, about these buffers that can buffer the protons. Bicarbonate is definitely one, phosphate is another, variety of proteins, even hemoglobin. Your body is trying to maintain a constant pH, right? Homeostatic pH. We know what acidosis is, and metabolic acidosis, as we start to exercise with the curve, you get accumulation of hydrogen ion concentration in the blood above normal. We call that a metabolic acidosis. And alkalosis is obviously when the protons fall below what we deem a normal value. Tolerable limits of arterial blood pH and muscle pH at rest and exhaustion. In terms of arterial blood pH, tolerable limits around 6.9 to 7.5. You don't want to fall out of that range. Okay. In the muscle pH, somewhere around 7.10, and you'll certainly reach exhaustion if your pH in the muscle is about 6.63. Okay. Let's spoke about that. I'll go back to the next slide though, but this one here is just showing you some data for some runners here, looking at, this is real data looking at muscle pH and blood pH, and you can see this is blood and muscle pH and lactate concentration 5 minutes after a 400-meter run. And you can see in particular with their muscle pH values here, they're very, very low. close to exhaustion. We said 6.63, you're going to be in exhaustion. Okay, and the average was 6.64 for these guys here. Okay, this is 5 minutes after a 400-meter run. Okay. Last slide, I'll talk about effects of active and passive recovery on blood lactate levels. You know, is active recovery better than passive recovery? Yes, it is. Why do you think it would be? This, for example, this graph is showing you that for any for any time in recovery, their blood lactate levels are less in active recovery as opposed to passive recovery. And why would that be? Obviously active, sorry, go ahead.
One of the lactate levels we want to active because you're still keeping the body moving.
Right.
So like you're getting ready to get rid of the lactate faster than.
How are you getting rid of it more? You're quite correct, you are.
How do you bring it back into
It's possibly you could be converting it back to pyruvate via the liver, gluconeogenesis, or the slow twitch muscle fibers starting to use it as fuel. That's possible. I'm thinking more of a, you're quite simple, more of a simpler idea, kind of along the lines of you. You're increasing your blood, you're keeping your blood flow going. All right? If you're keeping your blood flow going, you're going to flush out the metabolic waste products, not only lactate, but histamine, potassium, etc. Okay? So that's why obviously active recovery is better than passive recovery. And on those, I think that, oh, not quite. Last slide, this is the last slide. Last slide. Respiratory regulation methodology just continued here. So those excess protons, which obviously results in a decreased pH that we've spoken about this before, it impairs muscle contractility and ATP generation. Important, the respiratory and the renal systems help regulate acid-base balance. We've already spoken really how the respiratory system does that, right? So I've just covered it off. Getting rid of the CO2 and O2 by increasing minute ventilation, that's what we mean by the respiratory regulation. That's very much a short term. The long-term regulation to regulate acid-base balance is fairly involved, we don't have to worry about it in this class, is the renal system, the kidneys. The kidneys can actually excrete a tremendous amount of protons. It's a fairly involved process, it's a long-term solution, and that kicks in. Certainly when the respiratory system stops, so to speak. We've already spoken about how those protons can stimulate respiratory centers to remove CO2, etc. We spoke about the bicarbonate ions that conduct protons to prevent acidosis. And on those, that's it. Okay. So on Monday, we're going to have 2 quizzes. Okay, we're going to have one on the first lecture. We finished off today on the respiratory stuff, right? And then you'll have a quiz on this lecture. Okay? And then we'll be back on track.